And so that's where we're going to start. And these practice problems that I have here are posted to Canvas under the Chapter 2 module. And we'll start with the first one. Can everybody see my screen where it says Chemistry 3101?
Yeah.
Chapter 2 practice. Okay, good. All right, so it says here that Tamiflu, the most effective antiviral drug used to treat avian influenza, has the following structure. Identify the functional groups in Tamiflu. Is there anybody who can identify any functional groups in Tamiflu? Could anybody identify any of the functional groups in Tamiflu?
There's a carbonyl.
There's a carbonyl. There's two carbonyls in here, but a carbonyl is not a functional group. So a carbonyl can be, a carbonyl by itself is just a carbon doubly bound to oxygen like this. That's a carbonyl. So we have a carbonyl here and a carbonyl here, but the carbonyls are part of two different functional groups in this molecule.
Is the carbonyl on the left, would that be like a secondary amide?
Yeah, that's a secondary amide right here. So somebody says this is an amide.
Amide?
Yeah, you can call it an amide. You can call it whatever you want, as long as I know what you're saying. Yeah, so we have a secondary amide here. And then here, somebody said an ester. There is an ester here, okay? So this is an ester. Now, it might be a knee-jerk reaction to just say, well, I have the carbon with a double bond to oxygen. That's a ketone. That is not a ketone, okay? A ketone is when I have a carbonyl sandwiched between two R groups. Oxygen is not a carbon, so that is not an R group. So this is an ester. Are there any others in here?
An amine?
Yeah, there's definitely an amine here, isn't there?
Yeah.
So this would be a primary amine. Yep, absolutely. There's two more.
Would you technically call the double bond within the ring? Could you call that an alkene, or is it part of something greater?
No, that's definitely just an alkene, right?
All right.
Yeah, I can see where you might be going. You might think, okay, well, if I have this, right, 3 double bonds, that's aromatic, okay? But when you just have one double bond in the ring like this, that's an alkene, so you're absolutely correct. And there's one more, I'll help you out with it. I see somebody wrote it in here. Courtney says an ether, and she's absolutely correct. There's an ether. There's an ether. Let me use a red pen. There's an ether right here, right? You have an oxygen sandwiched between two R groups, so this is an ether here. All right. I'll just help you with this one. We'll go through this one. This is aspartame. Everybody consumes aspartame, right? It's found in sugar-free gum and Diet Coke and Coke Zero, things like that. Well, you can see that we have a functional group here that I'm circling in red. Could anybody identify that functional group, the one I just circled in red?
It's carboxylic acid.
Yeah, that's a carboxylic acid, absolutely. Now, let me see here. Go back. Okay. Oh. That is new. Try again. Okay, so here we have a carboxylic acid. So there we have a carboxylic acid. Over here, could anybody identify this one?
Would that be an amine?
Absolutely, that's an amine, yep. I see somebody said an aromatic. Yes, there's an aromatic here. Aromatic, yep. And the other ones are, we have an amide right here. So this is an amide. And then the last one is, there's one here. And this is, well, I guess I should put that carbons in there, but this here is an ester. So you have an ester here. All right, so that's a little bit of practice with some functional groups, and let's quit that for now, and let's go back to chapter 2, and we're going to go back to where we ended off, and that was talking about formal charges in resonance. This is where we ended off. Okay, just want to double check here. Yep, okay, good. So section 2.9 of chapter 2, and let's get to it. Formal charges in resonance. Last class, we spent quite a bit of time talking about resonance structures, and we looked at curved arrows, and we said that when you have a double-headed arrow like these ones that are shown in here, that those arrows represent the flow of two electrons. And so when using curved arrows to show resonance, structures will often carry a formal charge that must be shown. You can see the two arrows. The first one is going from a lone pair because the tail of an arrow will always start on a pair of electrons, and the head of the arrow is ending up between the oxygen and the carbon. That tells me that when I draw the other resonance contributor, what I'm trying to draw here, there's going to be a double bond between the carbon and the oxygen, isn't there? And instead of being two lone pairs in that oxygen, there will only be one, like that. And I'm going to draw the rest of the molecule like that. Now you notice that I didn't put this double bond there, and the reason why is because that the two electrons in that pi bond have moved, haven't they? They started out here. Now the tail of this arrow doesn't look like, it's not touching the pi bond, right? On the slide, it's not physically touching that, but we know that it's the pi bond that's going to move. We don't break sigma bonds in a resonance structure, do we? So the pi bond is the one that's going to move. And you see that the head of the arrow is not ending up between two atoms, but it's ending up on an atom. It's ending up on that carbon. So we put the pair of electrons, oh, let me change my font. We put the pair of electrons, oops, I was supposed to ask you that. We put the pair of electrons there like that. Now we have two formal charges in this resonance structure. Now, obviously, there's a negative charge here. And if you're wondering, like, hey, Mr. Dion, how could you have a negative charge? Because this carbon only has a lone pair and two bonds. Well, that's not true. This carbon has a lone pair and three bonds. The third bond is not shown because this is a bond line structure. It is implied that there is a hydrogen there, and the hydrogen is still here. Okay, and so that is why we have a negative charge on that carbon. Now, if the overall charge of this molecule is 0, then the charge of the resonance contributor is going to be 0. So that tells us that if we have a negative charge, we have to have one positive charge to balance that out. Can anybody tell me where the positive charge will be in this resonance contributor?
On the oxygen?
Absolutely, right? Because when oxygen has three bonds in one lone pair, it has a positive charge. You go all the way back to General Chemistry 2, okay? Many of you took General Chemistry 2 last semester. How many times did you write out hydronium when you studied acids and bases? Maybe Avogadro's number of time? Well, you know the structure of hydronium, and the oxygen in hydronium has three bonds in one lone pair, and it's got a positive charge. So nothing new there. All right, so drawing resonance contributors and recognizing formal charges. Well, here's a David Klein nugget here, and that's section 2.10, which is using pattern recognition to write out resonance structures. And he says there are 5 general bonding patterns in which resonance occurs. You have to learn how to recognize all of these. Now, at first, it's just like you're learning everything in life. Like at first, you might be a little bit slow with it. You're like, okay, which rule am I looking at here? Which pattern, sorry. And eventually, you'll just start to recognize it the more practice that you get. So here are the 5 general bonding patterns, and we're going to look at all 5 of these in detail. The first one is an allylic lone pair, represented here. The second one is an allylic carbocation, shown here. The next is a lone pair of electrons adjacent to a carbocation, shown in the third box. A pi bond between two atoms with different electronegativities. If you look at the fourth box, you can see oxygen and carbon, they have different electronegativities, obviously. And then the last one is conjugated bonds in a pi ring, right? So, or sorry, conjugated pi bonds in a ring. So that's a aromatic. Okay, so an aromatic. So we're going to look at all 5 of these in gory detail. But before we really get into the nuts and bolts of allylic lone pairs and allylic carbocations, the first 2, we need to qualify what does allylic mean, right? What does allylic mean? It's a new word for most of you, I'm sure. And there's 2 words that you need to know, vinyl and allyl, and they're just positions that I'm going to talk about all the time in organic chemistry. So if we have a double bond, right, we have all kinds of molecules in organic chemistry that have double bonds, right? The carbons that are actually involved in the double bond, the carbons that have the pi bond attached to each of them, those are called vinylic carbons, or we call them vinylic positions. You could say either one. You could say, hey, it's a vinylic carbon, it's a vinylic position. If you go 1 carbon away from the vinylic positions, now in this molecule, you can see that there's actually 4 vinylic positions, so 4 carbons next to those vinylic positions, we call those allylic positions. And we're going to be concerned with allylic positions a lot because they're involved in resonance. Now it says here that we look for allylic lone pairs, again, because they're going to be resonance delocalized, or another way we could say it is just they're involved in resonance, right? And that's what the major focus of today's lecture will be. If we look at the two lone pairs in this structure here at the bottom, we have two lone pairs, both in green boxes. You see the one on the top is not allylic, but the second one is allylic. Now, why would the second one be allylic? Because if we look at that lone pair, right, think about an allylic position here. You have the allylic position, a single bond, then a double bond. And the same thing is true for this lone pair. You have the lone pair, a single bond, and a double bond. You cannot do the same pattern for this lone pair here. You have to go a lone pair, single bond, then a double bond, right? And you're like, well, what if you went the other way? Then you'd have lone pair, single bond, single bond, single bond. So the pair on the top is not allylic. So you have a lone pair, single bond, and then a double bond, and that qualifies as an allylic lone pair. And we'll see that many times throughout this class. In fact, it says all of the lone pairs drawn in all of these examples are allylic. Now, when we have an allylic lone pair, we have to use not one, but two curved arrows to show the delocalization or the movement of the electrons, okay, of the allylic lone pair. Well, normally when we draw resonance structures, we draw them horizontally. It's just convention. You know, I told you put a square bracket and you use the resonance arrow like that. But since I have all five of these lined up like this, I'm going to be a little unorthodox, and I'm going to put my resonance open bracket here like this, and then I'm going to draw a curved, my resonance arrow like that. Now let me show you what the curved arrows would be for this one, and I'm going to go over the first one slowly. The first lone pair is an allylic lone pair because it goes lone pair, single bond, double bond, right? And that is the requirement for an allylic lone pair. How would we draw the curved arrows to show the resonance contributor? The way we would do it is this. We start with our arrow on the tail of the arrow on the lone pair, because the tail of an arrow always starts on a pair of electrons. And we're going to put the head of the arrow between these two carbon atoms, this carbon atom and this carbon atom. But if we were to just stop there, then this carbon would exceed the octet rule, wouldn't it? It would have 5 bonds. And if you're like, no, it would have 4 bonds. No, it would have 5 because there is a hydrogen here that is implied. This is a bond line structure. And so because that carbon would exceed the octet rule, we have to take the pi bond and we're going to break that, and we're going to take that lone pair and we're going to put it on this carbon on the end. So our other resonance contributor would look like this. We'd have the double bond on the right-hand side, and our lone pair would be over there like that. So that's our resonance contributor, like this. If we look at the second one, you can see that we have 2 allylic lone pairs. We're only going to move one of them, doesn't matter which one, but you can see it goes lone pair, single bond, double bond. So how am I going to do it? I'm going to draw the tail on the lone pair. It's going to go in between the carbon and the oxygen, which would cause the carbon to exceed the octet rule. So the pi bond is going to break. Remember, a pi bond is weaker than a sigma bond, and we don't break sigma bonds in resonance structures, and therefore we would end up with something that looks like this. And this is similar to the one that we drew at the beginning of class, okay? There we go. We have a negative charge here and a positive charge here like this. Let me just stop for a second here and say something to you, and that is, you know, if you're just sitting there watching me passively, I mean, everybody learns the way they learn. If you just are sitting there, you know, having breakfast or whatever and listening to me yammer on, that's fine. No problem with that. You do what you got to do. But if I can make a recommendation, the only way to master organic chemistry is to have pencil and paper, to let your pencil touch the paper and physically draw these. Because if you expect to be able to recognize resonance structures without being able to draw them, it will be exceedingly difficult. Okay, so I recommend from now until May, always have some scratch paper with you, a pencil, or the notes printed out, and follow along with me in order to maximize your time in lecture. Well, if we look at this ester here, you can see there's a couple of lone pairs that are left out, but we have an allylic lone pair here, don't we, right? This one here, we have a lone pair, single bond, double bond. So let's draw the resonance contributor there, and I'm going to speed up now. It would look something like this. We would draw our curved arrows like that, and then we would end up with a resonance contributor that's going to look like this. The oxygen will have 3 lone pairs and a single bond, so it will be negatively charged. We'll have a double bond here to our oxygen, which will have a positive charge. Same thing on the next one. We're missing one lone pair that's left out here, but we do have an allylic lone pair. We're going to draw the curved arrow. We're going to put the pi bond and move those electrons up there like this. I've got my open bracket. So my nitrogen is going to have 2 bonds and 2 lone pairs. It will be negatively charged like that. And then I'm going to have a double bond here like this. And in the final one, it's an amide. Same old thing, and we're going to talk about amides in detail at the, oops, that arrow's kind of ugly. We're going to talk about amides in detail at the very end of this lecture, but you read the chapter before coming to class today, so you know that. And here we go, we have our oxygen, we have our 3 lone pairs, like that. Double bond to our nitrogen, and oops, there we go, we have a positive charge like this. Now notice again that the charge of the initial resonance contributor for all of these is maintained when we draw the next resonance contributor, the other resonance contributor, when we show the delocalization of the allylic lone pair, right? This one has a negative charge, so this has to have a negative charge, right? This one is neutral, so this one has to be neutral overall. All right, give me a thumbs up if you follow me on some resonance arrows, because we're going to keep looking at pattern number 1, but we're going to move on from here a little bit. Just reinforce some of the things that I've already said. Okay. All right. Here we go. It says when the atom with the allylic lone pair has a negative charge, the charge is going to be delocalized. We've looked at that. Okay, so the charge is going to move around. If the allylic atom is neutral, it's going to become positive, and the atom receiving the lone pair will become negative. Now, these are rules that I don't like to memorize per se, but they could come in handy when you're learning. I think the best thing to do is just recognize, bonding patterns and lone pairs and bonds, and know when you have a positive charge and a negative charge on an atom. Let's move on from there to allylic carbocations. We've looked at, we've seen an allylic anion, and I didn't refer to that specifically, but we've seen that. But if we have an allylic carbocation, we only need one curved arrow to show resonance. And here's the example of an allylic carbocation. We have the tail of our arrow starting on the pi bond, and then the electrons are going to go between this carbon and form a new pi bond. Okay. Now, if that happens, that means that this carbon here is going to become electron deficient, and it's going to have a positive charge. Let me prove it to you. If we draw in all the hydrogens in this structure, right, we have 1 here, we have 2 here, and we have 1, 2 here, right? Because this is a carbocation. When carbon has only 3 bonds and no lone pair, it's got a positive charge. So look what happens. Now this carbon has 4 bonds, 2 to hydrogen, the sigma and the pi. This carbon still has 4 bonds, but this carbon only has 3 bonds now. And so that is why it becomes a carbocation. All right. If there are multiple double bonds conjugated, then multiple contributors are possible. They are drawn by moving 1 electron pair at a time. So when we see the word conjugated, I can break this down for you really simply. Conjugated in organic chemistry just means double, single, double, single, double, single, double, single. Okay, whenever you see that, if you have, any kind of organic molecule and it goes double bond, single bond, double bond, single bond, double, that's what we call conjugation. Okay, so you see that in this molecule here, we have double, single, right? They just alternate. That's all conjugation means. If you have a conjugated molecule, then we can have more than one resonance contributor. And so a student last class asked me an interesting question. They said, well, how many resonance contributors are there for a molecule? Is it usually 2, or is it 3, or is it 4? And the answer is it depends on the molecule. There's no way to answer that question directly. And so it varies. But you see here that we have a positive charge on the far left-hand side of the molecule. Let's think. If I move these 2 electrons from that pi bond over here, okay, then this carbon that only had 1 hydrogen attached to it, it still only has 1 hydrogen, so now it's going to have a positive charge, right? And then I can keep moving the electrons around. If I move these 2 electrons, then they're going to end up here, but this carbon that only had 1 hydrogen is going to have a positive charge. Give me a thumbs up if you just follow me on the concept. You're like, I'm going to need to practice this, right? All right, good. The main thing is that you just at least follow me on the concept, because resonance takes a lot of practice. It takes a lot of practice to master the concept of resonance. Well, another pattern that we saw is a lone pair adjacent to a carbocation. This one kind of makes sense. You know, you can think about it the way David Klein describes it in the book. He says, well, if you have a carbocation, you've kind of got a hole, right, in your molecule where there's no electron density. So if you have a lone pair on the atom next to it, you can just take that lone pair and you can dump it in there, right? You just dump it in and then make a double bond, and now you're going to fill up that hole. And so in this case, the positive and negative charge will go away in this molecule. In the next example, the one below, we have a positive charge here. We have a lone pair. We make a double bond. This positive charge disappears. Now, overall, this molecule or this contributor was positive. So that means that this one is going to be positive there. All right, let's move on. And let's see here. It says a pi bond between atoms of different electronegativity. So if we have two atoms with different electronegativity, obviously oxygen has an electronegativity of 3.5. Carbon has an electronegativity of 2.5. I asked you to memorize these in the first chapter. And so since we have an oxygen and a carbon, and we have a pi bond in between them, if you have your microphone on, if you could mute it, that would be great. Since we have a pi bond between them, we can take that pi bond and break it, and we can delocalize those electrons, put them up on the oxygen, so that the oxygen has a negative charge and the carbon has a positive charge. Now, if you're an astute student, which I know you all are, you might be asking, like, why, Mr. Dion, why would you do this? Why would you take a molecule that has no charge, and why would you draw something that's got two charges next to each other? Well, the reason why is because we're just starting the class out, and the reason why we learn resonance is because it can help us understand what? Reactivity. And that's where we're going in this class, right? We want to look at lots of reactions, and in order for you to understand reactivity, you have to understand resonance and resonance structures, all right? So you have to be, confident in your ability to understand or to draw resonance structures and recognize them. Anyhow, last one is conjugated pi bonds in a ring. So this is just an aromatic system, just like an aromatic functional group that I asked you to memorize. Each atom in the ring has an unhybridized p orbital that can overlap with its neighbors. Why would that be? Because each one of the carbon atoms, all 6 of them, could anybody tell me what the hybridization of each one of the 6 carbons in this molecule would be? What's the hybridization of the carbon that I drew the arrow towards?
Would it be sp2 hybridized?
Absolutely, yeah. Right, that's something that we learned. I mean, we talked about how when carbon has 3 sigma bonds and a pi bond, it's sp2 hybridized. We talked about steric number, right? The steric number of this carbon is 3, it's sp2 hybridized. However you want to slice it, every single one of the carbons in an aromatic ring is sp2 hybridized. That means each one of them has an unhybridized p orbital. Now, this is really Mr. Dion grasping at straws artist rendition here. But the idea is that each one of those carbons has a p orbital, okay? And those p orbitals all are overlapping like this. And so the electrons can kind of move around them like a conduit, right? Like wire through a conduit. And if you're like, I'm not quite sure about these p orbitals overlapping, we're going to look at that concept again before this chapter is over. The pi bonds can be pushed over by one position, clockwise or counterclockwise. It doesn't matter. You end up with the same result. So let's get back to resonance here. Let me delete this. So the idea is when we have an aromatic ring, we can push all 3 of the pi bonds with 3 arrows. And you see how the pi bonds were here, here, and here. Now they've moved over here. But remember, these molecules represent the exact same thing. Now, when it's saying that you could rotate or move the arrows in the opposite direction, look, if I was to draw this molecule, let me erase this, okay? If I erase this and I draw the aromatic ring the same way it is drawn here, and I push the arrows in the opposite direction. So you see how here they're kind of going counterclockwise, if you will. If we draw them like this, and like this, you're still going to end up with this, okay? Don't believe me? Draw it out, and you'll see that it's true. something that scientists or organic chemists do oftentimes, and I'm sure that if you've perused the internet or our textbook maybe, you've seen this, is oftentimes we'll draw an aromatic ring like this. Okay, we'll draw a hexagon and then we'll just draw a circle in the middle like that. And the reason we draw that circle in the middle is to just show that, you know, when we draw this, it's not exactly correct, right? When we draw this, it's not exactly correct either, right? We know that all those electrons in those 3 pi bonds are delocalized, and so they can move around the ring. So we represent it with just a circle around like that. Now, I won't use that a ton in chemistry, in organic chemistry 1 or organic chemistry 2. I don't use it a lot, but if you peruse the internet, and a lot of my students like to look things up on the internet, then you might see it there. So somebody's asking me about the carbons in the aromatic ring, if they're sp3. Are they sp3 because there is a hydrogen not drawn? So these are bond line structures, right? So there is a hydrogen on each carbon that's not drawn, okay? In a bond line structure, we leave all the hydrogens out. So there's one here, 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 and there's one here, right? Every single one of these molecules has 6 bonds to hydrogen. But we went over hybridization in chapter 1, right? We have a sigma bond here, we have a sigma bond here, and we have a sigma bond here, and then here we have a pi bond. So when we have 3 sigmas and a pi bond, the carbon atom is sp2 hybridized. All right, let's move on from there, and let's try a practice problem. So this is where it would be handy to print out the slides and give it the old college try. So I'm going to walk through this one with you. This is where it would be beneficial for us to be in the physical classroom, because I like to walk around and see what the resonance structures my students are drawing. But I'll just ask my students, does anybody have an idea where we might start with this? You know, is there any resonance contributor anybody sees?
I started with the nitrogen on the top.
Yeah, me too. Yeah, because you have a lone pair next to a positive charge. So you could take that lone pair and you could fill in, right, that positive charge. Now you still end up with a positive charge, but now the carbon at least is going to have an octet, won't it? Right? So we could do that. Let's draw that out. Now I'm not Mr. 7-membered ring. I'm not the cat's meow at drawing 7-membered rings, but I do what I can to earn a living. Okay. There we go. I guess that's okay. Anyhow, there we go. We have this over here. We have a double bond. We have our oxygen with a negative charge like this. And now we're going to have a positive charge on the nitrogen and no charge on the carbon. So that's one resonance contributor. Absolutely. That's a beaut, you know. Are there any other resonance contributors that we could draw? Well, in the interest of time, I'll say, well, look, we have an allylic lone pair right here. Any one of these 3 lone pairs on the oxygen is allylic, right? Because it's, right, it goes lone pair, single bond, double bond. So we could draw the resonance contributor for an allylic lone pair. Let's try that. We do this and this like that. Let's draw the resonance contributor that we would get. And let me just, again, you know what I should do? I sound like my father. You know what I should do? I should just copy and paste this. There we go, copy, and let's see if I can get this to work. There we go, something like this. Oops, playing with fire, Mr. Dion. You gotta be careful. Let me just try to doctor this up here for you guys. There we go, doesn't look too bad. So we have our double bond here, and now we have a lone pair here. Now that you can see that we've got another allylic lone pair, don't we? Right, we've got a lone pair here, single bond, double bond, so we could draw some curved arrows for that. I'm drawing them all in different colors. Obviously, you don't have to do that. But we could draw a resonance contributor like this, and that would actually be the last one. So let me try using this trick. Where's this thing? There we go. If I copy that, try. Come on. There we go. All right, let me get my eraser here. Eraser. And there we go. And we'll erase this pi bond. And then what we would end up with is we would have a pi bond here, and we would have a lone pair. And then we have a molecule with no charge, right? So those would be all of the resonance contributors for this molecule. There we go. Now, if you're like, boy, I'm not sure, Mr. Dion, this is interesting. There's lots of arrows here. They're pretty. How would you master this? I would go into the Canvas page. I would go into the Chapter 2 module. I have a whole list of practice problems there, a big list. Okay. If you start at the beginning of the chapter, it's going to ease you into these kinds of problems, like a frog in boiling water. Okay. You start out with warm water and the frog won't jump out, right? Anyhow, so that is what I recommend, is doing every single practice problem, not 90% of them, 100% of them. It's going to take a while. Yes, it will. Okay. Let's talk about assessing resonance structures. And if you're wondering, what does this mean? Well, let me explain it to you. If you look at let's go back here. If you look at these resonance structures, they're all very beautiful. They're all very pretty. They're all correct. Okay, there's nothing wrong with any of them. But some of them are going to contribute more overall to the actual resonance hybrid, to the whole. So some of these are going to contribute more than others will. Now, I don't know why I circled that one because, but anyhow, some of them are going to contribute more than other. And maybe I have it summarized better here. It says many molecules have many resonance contributors, where not all resonance structures contribute equally. And there's some rules, and again, this is invented by David Klein. There's some great rules that you can follow here so you can understand, like, hey, is this resonance structure worth a darn? Okay, is this important? Do I have to, is this important for the reactivity of this molecule? Yes or no? And following these rules, you will be able to make a quick assessment. Okay, rule number 1. The most significant resonance forms have the greatest number of filled octets. You look at these two resonance structures here. You know what would be my knee-jerk reaction, and what was my knee-jerk reaction way back in 1995 when I was learning this? I said, okay, well, carbon has got a positive charge over here, and oxygen has a positive charge over here. Carbon is less electronegative than oxygen. This should be the major resonance contributor, but I was wrong, okay? I was wrong, okay? I was incorrect. And the reason why this is a minor contributor is because this carbon doesn't have a full octet, does it? It's only surrounded by 6 electrons. 1, 2, 3, 4, 5, 6. The oxygen has an octet, 1, 2, 3, 4, 5, 6, 7, 8, but the carbon doesn't. When I move the lone pair, one of the lone pairs from the oxygen in between the oxygen and the carbon, now you can see that both the oxygen and the carbon have filled octets. And so when you have the most filled octets, that's going to be your greatest contributor, or your most significant resonance form. That's rule number 1. Rule number 2, the structure with fewer formal charges is the one that's going to be the most significant. Well, that kind of makes sense, right? We usually try to draw molecules without charge. So if we look at these 3 resonance contributors here, you see the first one has no charge, so it's going to be the most significant. The next ones both have charges, right? Oh yeah, the answer is on here. I was going to ask you why this one is a greater contributor than the last one, but the answer is on here for you. And the reason is, if you look at the carbons and the nitrogens in this resonance contributor, they all have complete octets, whereas here we have a carbocation, doesn't have a complete octet. And so these are actually ordered, right? This would be the most significant, this would be the second most significant, and this would be the third most significant. Okay, that's the second rule. Rule number 3, a structure with a negative charge on a more electronegative atom will be more significant, and vice versa. Now, if you're wondering, hey, Mr. Dion, didn't you just argue something about octets in the first rule when I'm talking about carbon and oxygen? Well, hold the phone, because in both of these resonance contributors shown right here, the oxygen and the carbons, they always have complete octets in both of these resonance contributors. However, the difference between them is in the first one, the negative charge is on an oxygen, and in the second one, the negative charge is on a carbon. So the war is won by the oxygen, right, which is the second most electronegative element on the periodic table. Here's just an, this is a protonated amide anyhow, that's neither here nor there, but if we look at these 2 resonance contributors here, I have a positive charge on an oxygen versus a positive charge on a nitrogen. The first rule doesn't apply, because the oxygen and the nitrogen in both of these contributors have complete octets. And so the major one is going to be the one that has the positive charge on nitrogen, because nitrogen is less electronegative than oxygen. Give me a thumbs up if you follow me on the concept of rule number 3. The rules, right? Quit stalling, man. Tell us the rules. All right, great. Okay. And I promise you, we've only got one more rule, and this one's I don't like to use the word easy in organic chemistry class because organic chemistry is not easy. If it was easy, everybody on the street would be able to do it. Rule number 4 is this. If the compound has an overall formal charge, you kind of focus on drawing resonance forms that only show the delocalization of that charge. You know what? There's an easier way to state this rule, and that would be this. Avoid making new charges. So don't go making a bunch of new charges for nothing. Here we have one negative charge. Here we have one negative charge. You know, I mean, is there anything technically wrong with what's here? The answer is no, but you have 2 negative charges and a positive charge. And when we can get away with only 1 negative, so the answer is we just don't make more charges for nothing. Okay, we don't just create charges out of thin air. That's rule number 4. Now this is where, you know, sometimes students will get a little frustrated with organic chemistry. Not all, but some, because they'll say, well, you know, if there's, you know, nothing technically wrong here, well, that is one of the things that separates organic chemistry from general chemistry 1 and general chemistry 2. No calculators, right? You have to kind of use your knowledge and your understanding of the subject in order to solve problems. You know, if you go back to general chemistry 1, PV equals nRT. If I give you PV and N, of course you're going to be able to solve for T, right? You know the universal gas constant. You plug the numbers in, you get an answer, bada boom, bada bing. With organic chemistry, what you're going to find is you're going to learn rule upon rule upon rule, and then the more you practice, the more you get used to those rules, and then you'll be able to use all those rules to help you solve problems that involve things that maybe you've never even seen before, but you'll be able to use your knowledge to kind of get your way through it. Okay. Yeah, there we go. That's one of the things I like about organic chemistry, and that's what drew me to the subject in the first place. Is when I was a university student, just like you, I kind of felt like, hey, here's a class where I can actually use, as long as I understand it, I can usually figure my way through the problem. Okay. And that's what I still like about organic chemistry. Even my brother works in business. He's like a business tycoon, but he has a chemistry degree. And even he has to admit, 20 years later, he says, well, organic chemistry, it is logical. He'll always say that. He'll give me that much. Anyhow, let's take a look at some practice here. This comes from Practice the Skill 2.26. It says, draw the significant resonance forms for each compound below and indicate the major resonance form. All right, well, let's get going here. Pitter patter, let's get at her. If we start with this anion here, I'm going to start by drawing in the lone pairs, which are left out. And if you're wondering, Mr. Dion, are you always going to, you know, draw the molecule with or without lone pairs? The answer is depends on the situation. You need to know that when you see a nitrogen with 2 bonds and a negative charge, that there should be 2 lone pairs. You need to know how to just draw those in. Well, what do we recognize here is that we have an allylic lone pair, don't we? We have a lone pair single bond and a double bond. Let's go. Let's draw some curved arrows. Let's get to it. So we're going to start by drawing our first 2 curved arrows for our allylic lone pair. And let's draw what the molecule is going to look like. We're going to end up with something that looks like this. We didn't even touch these bonds, so I'll just draw them in. We're going to have a lone pair here. We're going to have a double bond here. And we're going to have our nitrogen. I'm going to draw the bond to the hydrogen explicitly and put the lone pair. Could anybody tell me where this negative charge went? And it's not a trick question. Where did that negative charge go?
On
the carbon to the, sorry.
No, go ahead. You can overlap each other. It's cool.
The carbon that now has the lone pair?
Yeah, absolutely. Yeah. By the way, you guys, if you want to, like, if 2 people talk at the same time, look, this is Microsoft Teams. It's no big deal. Okay. I know none of you are impolite people. You're all very polite. You don't want to, you know, interrupt anybody, but don't worry about it. Yeah, because we know there's a hydrogen there, right? So this carbon has 3 bonds and a lone pair. Therefore, it's got a negative charge. I'm going to remove those hydrogens because I don't need to draw them. We've mastered bond line drawings by now. Look, we have another allylic lone pair. We see the same damn stuff showing up time and time again in organic chemistry. It's going to happen again and again and again. So I promise that you are not wasting your time by investing it in learning the rules. We have another allylic lone pair. Let's draw the curved arrows. Let's draw what the next contributor will look like. I've formed a double bond here. I never touched this one. I didn't touch any of this stuff up here. I'll leave that all the same, but now I'm going to have a lone pair here, and there's going to be a negative charge because there is a hydrogen here. I'm not drawing it in because it's a bond line structure, but it's there. And then lastly, you can see that there's one more resonance contributor because we have another allylic lone pair. And if you're getting excited and thinking, hey, Mr. Dion, it's just the same thing over and over, good, get excited because it is the same thing over and over, okay? Once you recognize it, you'll be able to, you'll be like, I'll be able to spot you a million miles away, allylic lone pair, and you'll be 100% correct. So let's draw in this resonance contributor, and we're going to have a lone pair here, our nitrogen up there like that. And then, of course, we have our negative charge here. Now, there is, you could keep moving the electrons around because we have allylic lone pair again. But when you do that, you're going to get right back to here. And let me prove it to you. If you draw this curved arrow and this one here, it's going to take you right back to here, okay? So technically, the four structures that we have drawn here are all of the resonance contributors, okay? So out of these, if I number them for you, 1, 2, 3, 4, could anybody tell me which one would be the major contributor out of these four resonance structures?
The first one?
Yeah, absolutely. Yeah, the first one. I want to see what my other students write. Yeah, great. Kayla, Brandon, Skylar, they all typed in the exact same thing. They all said number 1. Vita, you're all correct. Right? How did you guys know that? Because you said, come on, Mr. Dion, it's a no-brainer. The negative charge is on a nitrogen. Nitrogen is more electronegative than carbon. All the other negative charges are on carbon, right? So very quickly, you can say, hey, this is the major one, right? I have 3 other resonance contributors. They're great. They're fine. They're beautiful. But that is going to be the most significant, the first one. All right, great. Good work. Well, let's try the next one. I'm going to go over this one a little quicker. Going to have to speed up a little bit. If we look at this molecule, we know that this nitrogen has 3 bonds and that it's neutral. Therefore, it's got to have a lone pair on it. Well, looky, looky. I've got a lone pair and I've got a positive charge next to it. So I could fill that in like this to make a double bond and put the positive charge on my nitrogen. Sorry, thinking 2 steps ahead here, which is what a good instructor should do. Should always think a little bit ahead of your students. Anyhow, so let me just stop thinking too hard and draw this resonance contributor. So here we go. Looks something like this. We're going to have a double bond here and a double bond here. So here's the question I wanted to ask. Could anybody tell me where the positive charge is now? And it's not a trick. Mr. Dion doth not like tricks. Mr. Dion is not into tricks.
Is it on the nitrogen?
Absolutely. That's where it is. Yes. I heard both of you say that. That's what I heard anyway. And yes, you're both correct that is where it is. Now, what's great about, well, I'm getting ahead of myself. Let's draw one more resonance contributor. And this one, we're going to move 2 curved arrows because we have a positive charge on the nitrogen, but we have double bonds that are in conjugation, right? Double, single, double, right? It goes double, single, and then a double. So let me show you how you could push 2 curved arrows to fill in, to delocalize the electrons again. And this is how we would do it. We would draw an arrow back here, and then we would push this arrow over here like this. Now, if you're not following me 100%, let me draw what we would end up with, and then we'll make an evaluation of what I've drawn. So I'll put the nitrogen here. Now it's got a lone pair. Now this is not a trick question, but I'd say it's tricky to explain things over Teams, especially when you can't point at the board for me. Could anybody tell me where the positive charge is now? Just describe it to the best of your ability.
Is it at the carbon
The
completely
bottom
opposite
left corner.
nitrogen?
Yes, the bottom left corner is what I heard somebody say. Right here. Oops. I'm going to use my highlighter. Right there. That's where the positive charge is. Okay, the positive charge moved here. And let's go back to our bond line structure. This carbon only had 1 hydrogen attached to it. Okay, we're not moving hydrogens around. We will see cases where we move hydrogens around, but that would involve the breaking of a sigma bond, and we're not there yet. Okay, and so since this carbon only has 3 bonds, it's got a positive charge. Okay, I got one more question for you. And this one might be tricky too, but we'll give it a shot. Could anybody tell me if I label these 1, 2, and 3, which one would be the major resonance contributor?
Would it be this?
Go ahead. Go with
The
your
first
original
one?
thought. Sorry, what's that?
Well, number 2 has the charge on the nitrogen instead of the carbon.
Yeah. Okay. Well, let's think about if you're right that it's number 2, but I think your rationale is incorrect. And maybe I'm misunderstanding you, but let me explain what I mean. Because you're talking about the charge on the nitrogen. But that wouldn't make sense if we said, well, it's because the positive charge is on a nitrogen, because in the other 2 contributors, the positive charge is on a carbon. And carbon is less electronegative than nitrogen. And so carbon is technically happier with a positive charge than a nitrogen is. But I see that a whole holy host, we got Miss Moore, Vita, Victoria, Devon, Sadie, I got Avogadro's number of students who typed in number 2. And the reason why, I'll just answer for them. The reason why is they said, the reason why number 2 is the most significant is because what? All octets are filled. Okay, give me a thumbs up if that rationale makes some sense to you. You're like, I still need to study it, Mr. Dion. Don't give me the quiz, after class today, but yeah. All right, good. Great. Okay, wunderbar. Well, we're going to move on to the last 2 sections, which won't take us very long. And I've taught this class many times. Am I missing some slides here? Sorry, let me look at my notes here. No, I just have the wrong number on something, I guess. Anyhow, okay, the resonance hybrid. The resonance hybrid is a whole section in our textbook. Okay? Every time I teach this class and I get to this slide, I kind of make like a dramatic pause like I'm doing right now. And the reason why is this. I am probably not going to ask you a lot of direct questions about the resonance hybrid. Okay? Not a lot of direct questions about the resonance hybrid. However, if you look at the list of practice problems that I have posted to Canvas, the ones that I handpicked from our textbook for you to do, okay, I included a bunch of questions about section 2.12. And you're like, why would you ask me to solve problems about it if you're not going to ask me about it on a quiz? Haha. The reason why is because historically, I always found it difficult to ask questions about the resonance hybrid on a paper exam. So back in the day, pre-COVID, when the students were actually sitting down with a pencil and a piece of paper and writing their physical quizzes, it was difficult for me to ask questions about this because I'll be honest with you, their answers were so crazy that they were just hard to read, hard to understand what my students were trying to tell me. So here's what I'm trying to get at. Just because I'm not going to ask you a bunch of direct questions about resonance hybrids on a quiz doesn't mean you don't have to understand it. Okay, I'm just kind of throwing you a little bone and saying, you know what, you guys, I'm not going to ask you a ton of direct questions about it, but I still want you to understand the concept. What's a hybrid? What's a hybrid car? Well, a hybrid car isn't an electric car. A hybrid car isn't a gasoline car. A hybrid car is a car that can run on gasoline or electricity, right? Just like we talked about the resonance hybrid during the last class, and I talked about the horse being crossed with a donkey to make a burro or a mule, or just the way that you make seedless fruit, right? How do we get grapes with no seeds? We cross a monocot and a dicot, okay? A hybrid is a representation of more than one thing, right? Gas and electric. So the resonance hybrid represents the pi bond of an allylic carbocation being delocalized over 3 atoms. What does that mean? You know how we drew this earlier on? This was nothing more than an allylic carbocation. It was one of the patterns we learned. I think it was, the second or third one anyhow. It escapes me right now. But we spent 5 minutes on this already today. But if you think about this, neither of these structures perfectly describe resonance, do they? We have to draw, and you're like, well, do any of these perfectly represent resonance, all these structures we're drawing today? No, That's why we have to draw a collection, because no individual resonance structure actually represents the entire resonance structure, okay? And in order for us to represent the entire resonance structure, we use what's called a resonance hybrid. And if you're like, what the hell is that thing, okay? Instead of drawing two pi bonds, one here and one here, we make a dashed bond, and that shows that the pi bond is actually spread out over the entire molecule, right? Because you have three p orbitals that are overlapping like this, so the electrons can go back and forth, right? If you will. And they're not vibrating, it's not what it is, but it's the best way I can explain it to you. Okay? So what I want you to do for the quiz is I want you to read through the section on the resonance hybrid. I want you to try those questions and make sure you at least have a working knowledge of what the resonance hybrid is when you step into the quiz, okay? It might be worth the value of one question on the entire quiz. So in the interest of time, I'm going to move on from there and talk about the last section. And this is what I meant. See, I have some numbering problems here. This should say section 2.13. Anyhow, let's go back here. This is the last section of chapter 2. If we have time at the end of class, we're going to try some more practice problems. Delocalized lone pairs. And if you're thinking, well, Mr. Dion, we already spent a bunch of time talking about delocalized lone pairs. I know this already. Let's talk about it a little bit more. When we have localized electrons, those are not in resonance. Let me show an example where we would have localized electrons. Let me give you a simple molecule, ammonia, NH3. This is a Lewis structure all of you drew in General Chemistry 1, okay? You see, there's a lone pair on the nitrogen. It's not allylic to anything. There's no way that that lone pair can participate in any resonance at all. Let me give you another example. Ever heard of this molecule? H2O, okay? There's two lone pairs on the oxygen, right? Those lone pairs are localized. They're not going anywhere. There is no resonance contributor that you can draw for a lone pair, either lone pair on a water molecule. Those are localized. They're stuck in one spot. Well, when I talk about delocalized, and I've used that word quite a bit, delocalized electrons are the ones that are involved in resonance, and they're more stable. Why would they be more stable? As I told you in the first lecture on chapter 2, electrons are high energy. If they can move, they will. If there's a place for electrons to move, my friends, they will. They're like hyperactive children. If you put them in a space, they're going to move in it, right? Okay? So when those electrons are delocalized, when they move around, what it does is it actually stabilizes the molecule. So that's a theme that's going to come up repeatedly in this class. You guys are going to answer questions to me, and you're going to say, well, this is more stable because it's got more resonance, blah, 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 so on and so forth. Well, let's talk more about this delocalization thing. In order for a pair of electrons to be delocalized, they've got to be adjacent to an atom with an unhybridized p orbital. Okay? And if you're like, did we see that today? Yeah, every time we saw this, there was an unhybridized p orbital. If we think about an amide and we look at the lone pair on the nitrogen of the amide, what's the hybridization of this oxygen here? See, you need to know chapter 1. The hybridization of this oxygen is sp2, and there is an unhybridized p orbital on it. The hybridization of this carbon is sp2. There's an unhybridized p orbital on it here. And so if this nitrogen, if I was to ask you, what's the hybridization of that nitrogen, okay? And if you're eating, put your spoon down because you're going to choke, okay? If I was to ask you, based on what I taught you in chapter 1, you'd say, that's sp3, Mr. Dion. Steric number's 4, sp3, buddy, okay? And here I'd have to say, no, it's not. This is actually sp2, and if you're like, why? Okay, why? The reason why is this. I just told you that electrons are hyperactive. If they can move, they will. So what happens is the lone pair on the nitrogen goes into a p orbital, and that way these three p orbitals can overlap and the electrons can move, okay? Or they can be delocalized, which is the more correct term to use. And if you're thinking, well, hey, Mr. Dion, didn't I already draw a resonance contributor for an amide? Didn't we do that? And I would say, absolutely we did, right? We drew this already. Okay, so let's talk about this even more. Oops, I keep doing that. If you look at these two resonance contributors, we drew these today already, but if you look at them, in one of the structures, right, based on what you learned in chapter 1, this nitrogen looks like it's sp3. I'll put it in quotations because it's not. And then here, the steric number is 3, so it looks like it's sp2, and you're like, damn it, crap, which one is it? Okay, well, the answer is, in order for that lone pair to be delocalized, the nitrogen would have to be sp2 hybridized, wouldn't it? It would have to have an unhybridized p orbital. And so the answer is the nitrogen must be sp2 hybridized. And in fact, the molecular geometry of that nitrogen is trigonal planar. So trigonal planar. Now this is where chemistry can get confusing sometimes, but if you look at this, you'd say, hey man, it's tetrahedral, but it's not. If you're a person who's a biology student and you've studied proteins and you've learned about, you know, secondary structure, alpha helix, beta pleated sheet, tertiary structure, a quaternary structure of enzymes and proteins, well, this is one of the reasons why proteins and enzymes have, you know, the conformations that they do. It's based on the hybridization of the nitrogen in an amide bond. And of course, when we link amino acids in a protein or a peptide, they're held together by amide bonds. If you just want to memorize it, okay, if you're like, Mr. Dion, come on, just cut me some slack, man. I need an easy way to get through this, okay? I'll tell you that if I had 10 seconds to teach this slide to you, I would say this. Memorize that the nitrogen of an amide is sp2, okay? Now, that's not the best way to do it, but I'd say if you only have 10 seconds to study, I'd tell you that. The next thing is this. And years ago, I gave an ACS exam in this class, and the first question on the ACS exam was what's covered on this slide. It was about the hybridization of the nitrogen in pyridine. So you know how we've drawn this molecule, like, I don't know, probably 10 times already. This molecule here, what I called an aromatic ring, this molecule has a name. It's called benzene, okay? If you replace one of the carbons in benzene with a nitrogen like this, you get a new molecule, and it's called pyridine. It smells really bad. Okay, you get pyridine. If we look at pyridine, and based on some of the rules that I taught you today, you'd say, hey, Mr. Dion, look, allylic lone pair, buddy. Lone pair, single bond, double bond. Bada boom, bada bing, draw the resonance structure. There's a problem with that one, okay? The easy way around it is this. I would say memorize that the nitrogen in pyridine is sp2 hybridized. Let me explain why it is. Why this is not a valid resonance structure. The reason why is because of this guy right here. There's already a pi bond in that nitrogen, isn't there? That tells me that that nitrogen already has an unhybridized p orbital on it, right? Right here. It's already got one. And it's going to overlap with all of the unhybridized p orbitals on all of the carbons, right? 1, 2, 3, 4, 5 carbon atoms. Okay? So there's already a p orbital on the nitrogen, so there can't be a second one to hold the lone pair. We have a steric number of 3 on the nitrogen. And if you're like, what is steric number? Well, I went over that in the first chapter. Okay, number of sigma bonds and number of lone pairs. So 1, 2, 3. It means it's sp2 hybridized, and therefore the lone pair resides in an a hybridized sp2 orbital. All right. And if you're like, I'm not following you 100%, Mr. Dion, what would you do? If I was you and I was like, I'm not following 100%, I would go to section 2.13. That's what section this is. And I would be sure to read it. Okay, it's not a long section. It's a very short section. All right, well, let's look at the last slide. And it just says, don't assume that a lone pair is delocalized just because it's next door to a pi bond. I have a lot of students who love rules of thumb or give me some quick and dirty rules. You know, this would be the rule right here. A general rule. When you have an atom that has both a pi bond and a lone pair attached to it, okay, both of them are not going to participate in resonance. Usually it's going to be the lone pair the pi bond that participates in resonance. And as always, if there's no p orbital next door to the lone pair, then it's going to be completely localized. So if we look at this molecule down here, you can see we have a lone pair here on this nitrogen, a lone pair here. Well, this lone pair is localized because it's not adjacent to anything that it could be it could form a resonance contributor. Whereas this lone pair is actually delocalized, right? This lone pair is delocalized. This nitrogen has no pi bond directly attached to it, but it is allylic, right? Lone pair, single bond, double bond. So that one is delocalized. It is involved in resonance. This lone pair here is not involved in resonance. Why? It's because the culprit is this right here, the pi bond on the nitrogen. So there's already a p orbital that's involved in the pi bond. And so that lone pair is not going to be involved in resonance. All right, well, that covers all of chapter 2. It's 9:01. We've got 3 hours left. So I thought we would try some practice problems. And if you go into Canvas and you look under the Chapter 2 module, you'll see that I posted the practice problems there. So if you have a tablet and you want to put them on your tablet, you could do that. If you have a printer at home and you want to print them out, probably, you know, I'm assuming that the sales of printers have gone up since the whole pandemic. You know, as a lot of people can't get to their offices or whatever where they used to print everything or photocopy stuff. Anyhow, sorry, let me get back to our lecture here. There we go. Okay, so this is question number 3. I'm going to give you a second to look at it. And while I'm doing that, I'll just kind of talk to you for a second. I have a really hard time being quiet in class. You know, when I'm supposed to be like, okay, you guys work for a second. It's very difficult for me to do that. I enjoy talking to my students. Anyhow, look, here's where we are. We're in chapter 2. We finished quiz 1. Okay? The class is not going to get easier from here on out. Okay? It's only going to get, you know, more and more complicated. And I'm not saying that to scare you or anything. What I'm saying that for is so that you understand, if you're thinking, you know, I'm having to put quite a bit of work into organic chemistry. That's totally normal. If you ask any friend or a loved one or, you know, another student who's gone on before you that you might know, and ask them about this class, if they were successful in organic chemistry, it takes a lot of time to master the content in organic chemistry. There's just no way around it. So don't ever think, oh, it's just me. I'm the only person who finds organic chemistry, you know, complex at times. Other times it's not, but that would be considered completely normal. Okay, it says here in question number 3, well, somebody says everyone I have talked to says they have failed it the first time around. Well, I've taught this class for years, and I can tell you that most people don't fail it, okay? Only a small number of people usually fail the class. All right, so here we go. Let's get started. It says draw 2 additional resonance structures for the following compound. You see that the carbon here on the end has a negative charge, so that tells us that there must be 2 hydrogens attached to it and a lone pair, right, in order for it to be negatively charged. I'm just going to remove all that spinach and make it even easier for myself and just draw in the lone pair. So here's the lone pair, and look what happens when I draw that lone pair in. I have a lone pair, a single bond, and a double bond. Okay, so I have an allylic lone pair. So I can start by drawing the tail of my arrow starting on the pair of electrons. It's going to go in between these 2 carbon atoms. If I was to stop here, then this carbon would have 5 bonds, wouldn't it? Because it's already got 1, 2, 3, 4. So that's impossible. And that means that I'm going to have to break this pi bond and put the lone pair on this carbon here, like that. Let's try drawing the resonance contributor. So it's going to look something like this, like that. And we're going to have our negative charge here. Could anybody describe to me how I would draw another resonance contributor for this?
Would you be breaking the triple bond with the nitrogen?
Yeah, I'm going to have to break one of the pi bonds on the between the carbon and the nitrogen, right? Yeah, so I have another allylic lone pair. Now, even though it's not a double bond, there's 2 pi bonds here, right? So I have lone pair single bond and I have a pi bond. So that's like it's allylic, right? So I can do something similar. I can put a double bond between the carbon and the next carbon and then break one of those bonds and put a lone pair on the nitrogen. And let's draw what we would get from that. We would end up with something that looks like this. So I'm going to draw this carbon here just to kind of help you, this carbon here. Maybe I'll draw it a different color. There we go. Just so you know it's there. And this is just for learning purposes only. Then I have a double bond to the nitrogen, and it's got 2 lone pairs. Could anybody tell me where the negative charge is now? And it's not a trick?
Nitrogen.
Absolutely. Absolutely. There we go. It's on the nitrogen. Perfect. Give me a thumbs up if you're like, I think I could draw that those resonance structures. Just watch me. Anyone? All right. Good, good. Okay, again, and I'm repeating myself like an old man here, but I'm in my 40s, so I've earned the right to do that. I recommend having a piece of paper and either, you know, printing this out or just following along and drawing on a piece of paper. Here we go. We have a molecule, and it says to draw 2 additional resonance structures for the following compound. Let me give you a second to look at this first before I start yammering on. And if you're way ahead, you could try drawing some resonance contributors for this guy too. Does anybody have an idea of where we might start? Or just one way we could, and it's not easy to describe it over Teams, trust me, I know.
With the negative charge on oxygen?
Yeah, we could try and move that around, yeah, for sure. We could
How
move
about
that
with the
around.
charge?
Sorry, go ahead.
How about with the positive charge first?
Yeah, so we can't move a positive charge, but we could move the positive charge.
The positive charge.
Sorry, repeat that.
Yeah, move that double bond next to the positive charge first, maybe.
So we can't break that. So what you're saying is to break this double bond or something like this, maybe. We can't do that because then we can't do that because then we would not have enough. We would create multiple charges on this nitrogen if we were to do something like that. Okay, we would create multiple charges then. Let me help you guys out. We have a positive charge here and we have a pair of electrons on this nitrogen. If we move this pair of electrons in between here to create a double bond, I'll just move down here a little bit. Then what we end up is something that looks like this. We have a triple bond here. And now the nitrogen on the far left has no charge because it's got 3 bonds and a lone pair. And then I didn't even touch the oxygen, so I'll leave that like this. Could anybody tell me where the positive charge is now?
The middle nitrogen?
Yeah.
The middle, exactly. It's on the central nitrogen, right? The positive charge is here. Okay, and then there's one more resonance contributor that we could draw. And that would be if we were to take this pair of electrons and move them here, but then if we were to leave all 3 of these here, then this nitrogen would exceed the octet rule. So I have to break these and put them over here. And then I end up with something that's going to look like this. So let me draw it out for you. I'll have something that looks like this. I'll have a double bond here, and I'll have a double bond here, like that. I'll have a negative charge on the nitrogen and a positive charge on this one here. And those are all of the resonance contributors for this molecule. Remember, we want to avoid making multiple charges. We don't do that. So having +2s and -2s, you're never going to see me ask you anything where you would ever have a resonance contributor where you have +2 or -2. Will never happen. Not in this lifetime. Okay, well, it's 9:10. In the interest of time, I'm just going to walk through one more with you here, and I'll do this one really quick. But here we have an allylic carbocation, and so we could draw a resonance contributor for that. Let's draw what we would end up with. And we end up with something that looks like this, where we have our oxygen here. We didn't touch this bond. And we have this, and then we have our carbocation out here. Another resonance contributor that we could draw, we could move these pairs of electrons back like this. And if you're wondering, you know, like, hey, Mr. Dion, couldn't you have just done this from the get-go with a different curved arrow? And the answer is yes. So I'll do it that way for you. And you can see I'm going to post the solutions to Canvas for you to look at. And you'll see that I did it a little bit differently in there. But in that case, you'd end up with something that looks like this, where you have the positive charge here. And then you could just fill that in like this to complete the octet on the carbon, and then you would end up with, oops, I find it hard to draw on a tablet sometimes. There we go. You'd end up with this where you have a positive charge here, and you have all this conjugated like that. Anyhow, there we have it. Could anybody tell me which one of these four is the most significant if I label them 1, 2, 3, and 4? Yeah, it's number 4. Thanks, Mackenzie. It's number 4, and it's because all octets are complete. Okay, so these practice problems that I posted here today, again, they're on Canvas. I will post the solutions today. I usually do that if I run it, if I know I'm going to be able to finish the chapter in class. I'll usually put a few extra practice problems. They are no better, they are no more indicative of what will be on the quiz than the actual problems in your textbook. They're not, there's nothing special about them. I just throw up some extra problems instead of just doing problems from the book. Some weeks I just do problems from the book. It depends, you know, week by week. I like to change things up. And the bottom line is that we're getting good practice in. That is the bottom line.